Don't miss out on our new videos by subscribing LogicHeap and pressing the bell icon.
Hello friends, welcome to LogicHeap. Today we are going to see how we can perform search operation in BST or a binary search tree. So this is a BST given to us following the condition of BST. Then we have a key that needs to be searched in this tree. So the key is 15 and the question is we need to find if 15 is there in this tree. We need to search for 15. If we get it, then we need to return the node having this key. If not found, then we'll return none. Okay, so this is a problem statement and this is our goal. So let's think about the logic, how we'll reach to it. Okay, so if I would have asked you without writing the code that you need to search 15 here and it is a BST. What is a BST? In the left subtree you'll have smaller values, in the right subtree you'll have greater values as compared to your node's key. So you'll start with 34, you'll start with root, you'll check if it is equals to 15. Of course, firstly you'll check it. See, here it is not. So what should you do? Where should you search 15? 15 cannot be in the right subtree because right subtree will have values greater than 34, right? So that is for sure that 15, if we'll be able to find, it must be in the left subtree. So now we have limited the search, we have made this problem small by just considering the left subtree, right? Next, what will you do? You'll check for 14. Okay, now in this subtree, this is like the root element. So you look for 14. If 14 is equals to 15, no. So 15 is greater than 14 in fact, right? So where should you go? Left hand side or right hand side of this tree? You'll go to the right side because only right side will contain values greater than 14, right? So 15, if we'll be able to find, it must be in this subtree. Again, we have shrunk the problem. We have made this problem smaller by just considering this tree. Now, this is like the root element of this small tree, right? You'll compare 16 and 15, okay? Now, 16 is greater. It means if 15 we'll be able to find, it must be in the left side. So now you have made this problem even more smaller. Now you'll check this tree's root, which is 15 only. So you'll check 15 and 15, yes, these are equal. So you will return this 15, like this node completely to the user. Okay, so that's how we move. We start with the root node. We compare root's value and the key. If they are equal, then we return the root node. If they are not, then we'll see we move to the left or to the right. Okay, once we move to the left subtree or to the right subtree, this becomes the new root node. We compare it with the key and every time we move like that. Okay, so that's the procedure. Let's just think how we can write its code. Okay, let's start writing the code. Code needs not to be the optimized one. You can simply write the logic that you have built, then you can optimize it later, right? So let's start. Firstly, when you will come here, what you are doing, you are checking these two things, right? The key and the root's value. So let's name this method as search. Okay, and we'll have root here, first parameter, and key. The first thing is, if root dot value is equals to key, then what you should return? Return root. Okay, now there's one more thing. If root is none, at any point if your root is none, what you should do? Let's say if root itself would have been none, okay, in that case you will not be able to find the key in this tree because root itself is none. In that case you will return none because you are not able to find 15 here. So one case, if root, okay, if root is none, return none. Clear? Now other thing is, if root dot value is less than key, okay, if root dot value is less than key, it means key is bigger. If key is bigger, it means you need to find it somewhere in the right subtree, okay. And in a way, now this problem is minimized to this. So whatever after searching from this tree I'll get, I'll return it. So what I'm saying, return search, okay, root dot right comma key. So now let's see what I have done here. Search root dot right, it means I am calling the same method again but with another tree. Which is that tree? It's the right subtree, because we know if key is greater than 34, it means you will be able to find it in the right subtree. And what is the root node of right subtree? It's root dot right, okay, and the key that I need to search for. Else what you will do, return search. If the key is smaller, then you need to look in the left subtree. So search root dot left and key. So for the left subtree, you need to provide the root element and the key to this search. Okay, so this is my method. This I can initially think of. Now let's see how it will work. Okay. Okay, so actually I wanted to tell you the recursion which is going inside. So that's why I have written this code 4 times, 4 copies of search method. So initially when you will call search method, you will pass root node. Okay, that's how I am denoting root node, and the key as 15. Okay, now if root is none, no. If root dot value is equals to key, no. If root dot value is less than key, no. So we'll go to else. Return search root dot left. So we are calling again this function, okay, and we are passing root dot left. Root dot left means this subtree, okay. Since key is lesser, we are sure that we'll get the result in the left subtree. So I am passing it the root node of the left subtree, which is 14. So see here, this is this method. Here root is now 14. Okay, root node is 14, key is 15. Since it has again called the search method, okay, but this time the values, the arguments are different. We are getting node as 14 and the key as 15. So this time root is none, no. Root dot value is equals to key, no. If root dot value is less than key, so key is 15 and root dot value is 14. So this condition becomes true. And we'll go to here, return search root dot right comma key, right? It means key is bigger. So our result could not be this side, we need to move this side. So this subtree, what is the root node of this subtree? This 16, okay. So again we are going to call the search method from here, okay. And this time what is your root node? It's 16 and the key is 15, right? Root is none, no. Root dot value is equals to key, no. Root dot value this time is 16 and key is 15, okay. So we'll go to else part. It means this is 16 and we need to look for 15, so it must be in the left subtree. So this time root dot left. What is root dot left? It's the root node of left subtree, which is 15. So now we are going to call it again search method. This time root is 15 and key is also 15. So this time this condition is going to be true if root dot value is equals to key. So we will return root, okay, we will return node 15. Now where it is going to get returned? So this goes to the point from where we called it. We called it from here. So this search value of it now becomes node 15, okay. Now this method is going to return this node 15, where it is going to return. So where this is going to return it? From where it got called? From here, okay. So here you got node 15 return node 15. So node 15. So we are going to return it. So here the value now becomes node 15. This is the result. So you'll return node 15 to the user. Okay guys, so again we are going to dry run the same code, but this time the key is 117, which is not there in the BST. So let's see how our code works when the key is not present. Okay, so we'll start from here. The key is 117 and the root node is 34. So here 117 is bigger, so we should look for the right subtree, right? So this condition is not there, this is not there. If root dot value is less than key, yes. So we'll again call the search function, but this time we'll pass the root node of this subtree, okay, and the key. So 100, node 100, and the key is 117, right? Again, see, 100 is there and the value is 117, which is greater. So we need to look to the right subtree. So like this one we need to consider. So here if root dot value is less than key, yes. So this becomes true, and we come inside return search root dot right. So this time the node is 115. Okay. Node is 115 and key is 117. Again you will check if this is none, if this is equal, both are not true. If root dot value is less than key, yes, still it is less than. So this time also we will go to the right of it. Clear? This time when you pass root dot right, so this was your root, and in the right what do you have? You have none. Okay, so in the root now you have none and key is 117. So you will come here. If root is none, yes, you will return none from here. Okay, so here you will return none. So this becomes none. This then pass here none. This then pass here none. So ultimately you get none as the result because 117 is not present in this tree. Now briefly I also wanted to talk about the time complexity. In case of binary search tree, search operation takes big O of h time. H is the height of the tree. So in case where your tree is properly balanced, if it is a balanced binary search tree, so what is balanced binary search tree? If the height of your left subtree and right subtree has no more difference than 1, then it is called a balanced binary search tree. If your tree is like that, in that case height becomes log n. Okay, this could be the minimum height possible of the tree having n elements. So in that case, in the best case, it will take log n. Okay, in the worst case, suppose your tree is skewed like this: 34, 15, 7, 6, 4, 2, 1. Let's say this is your binary search tree. Now it is following all the condition of binary search tree, but you can see if n, what is n here? 1, 2, 3, 4, 5, 6, 7. If n is 7, so you can see whatever is the number of nodes, that is the height of your binary search tree.